Somebody reply, last class in the introduction for manufacturing. So what is manufacturing, and then how this term manufacturing, we said that the term, two terms like manus and factors, which actually means that it is handmade. But then now when we think about manufacturing, we remember the big machines. So we think about factory automation, robots and industries. But in the beginning, it all started with what I've been doing with the hand. And also if you look at the importance of manufacturing, so a country's economy is based on the manufacturing. So if a country has to develop, so it has to be based on the manufacturing. Then we have also seen what is the importance of machining in all this scenario of manufacturing. So it says that in all manufacturing area, 80% it is about the machine tools. So in your subject, we are going to study about this metal cutting. And also when we looked at the development of machining technology, though what we see now is a modern technology, but it all began even right from the days of the Stone Age. So where people started using the implements, sharp implements. So they understood probably what we call today as the shear theory. So when the shear force, what we are going to apply, exceeds the shear strength of the material, so then actually the cutting will be starting. So thus, though they understood this principle or not, but they started using the sharp tools. I also gave you an example. When you want to cut an apple with a blunt knife and a sharp knife, so you can make the difference. So when you make it sharp, so all the force what you are going to apply concentrates at a particular either point or a line, depending upon the type of contact. And when it exceeds the shear strength of that material, so the cutting actually begins. So this is what we said. So those people understood that. And then we also have been talking about the Egyptian pyramids. So when they made those pyramids, so they used all the technologies what we have been talking about. And also Chinese were popular in using what is called as the bow drill. Then we have also quickly looked at some of the history who contributed for the development of the manufacturing. And we talked about the computer, which actually revolutionized the whole way how manufacturing has been done. So if computers are not there, we cannot have the CNC machines, we can't have robots, we can't talk about automation and all these things. So thus the computers have contributed a lot to manufacturing. And then we talked about what is called as an industry 4.0. So where we had different revolutions in manufacturing. So the first one is mechanization, the second one is mass production, and then the third one is computer and automation. And now we are in an age what is called as the fourth generation, where we are working in what is called as the cyber physical systems. So where the systems can interact with the human beings. So that is the level of automation what we are living in. So now we'll come to your subject, so where we talk about the metal cutting and machine tools. The course objectives, I don't know whether you have the syllabus book with you. So the course objectives will be to provide the students with the fundamental knowledge about the principles of metal cutting, and then to tell them about the practical applications, then to demonstrate the machining processes, and then to develop the knowledge and importance of the cutting parameters. So they play an important role, and also to make you to understand about the tool materials and cutting fluids. And obviously we are going to give you some of the problems, so where you have to solve so that you will understand some of these concepts. And then it says what are the course outcomes. So applying the cutting mechanics to metal machining based on the cutting force and power consumption. So probably when you become an engineer, if you are put on the shop floor, so you should be able to know what should be the material which you should use, what are the cutting tools which you need to use, and then what will be the power consumption and all these kind of things. And also your syllabus indicates that you should learn to operate lathe, milling machine, drilling machine, etc. So but that you need to do it practically in your workshops. So just if I teach here, you may not be able to achieve that goal, but maybe your colleges will take some interest in showing you the practical demonstration of these machining processes, and also probably they'll give you a training in operating these machines. Then selecting the right cutting tool materials and right processes. And then there is something more. So you will also be learning about the economics. So if I do this process, what will be the cost involved? So if I do this, which is more economical, so you should be able to understand those kind of concepts. And then towards the end, we have the last unit which talks about the jigs and fixtures, and then CNC machines. So you'll also will be learning them in this course. Then I think they'll hand over you the syllabus for your course. So the first unit, which we are going to start today, so that will be about the fundamentals of machining. So then the second unit is about the lathe machines, and the third unit about shaping, slotting and planing machines, and the fourth unit will be about the milling machines. Then the fifth unit will be about the finishing processes, and the sixth unit will talk about the jigs and fixtures and the CNC machine tools. The textbooks, probably if you want, you can note down these things. I'll give you 2-3, maybe a half a minute. So these are the textbooks which have been specified for you. Manufacturing Processes by J.P. Kaushik. And the other one is Manufacturing Processes, Manufacturing Technology by P.N. Rao. Manufacturing Process by J.P. Kaushik, Manufacturing Technology by P.N. Rao. You can note down. Any questions? The first unit. So about the metal cutting, about turning processes. So when you look at manufacturing processes, so we generally categorize them into three categories, like primary manufacturing process, secondary manufacturing processes, and tertiary manufacturing processes. Okay, in the primary manufacturing processes, so what we do generally is like forming, casting, where we are going to get the basic shape of the materials. So we are going to get the basic shape of the materials. So then in the secondary operations, so that is what we'll be talking about in this unit, basically involves the metal removal processes. So then we'll be dealing with the surface finish and other finishing operations, and the technology which is involved with the metal cutting process. So this is called as the secondary manufacturing processes. Then the tertiary manufacturing processes, so where it is called as the finishing process. So when you want to achieve very high surface finish, and also when you want the dimensions to be controlled very accurately within the required size and the tolerances, so we need to go for the tertiary operations. So where the amount of material removed will be very small, but we are going to achieve accurate dimensions and also the good surface finish, which is basically the requirement of the machine components. So the processes like grinding, polishing and honing will be coming under this type of tertiary manufacturing process. So if you want to categorize the manufacturing processes, so we can put them into three basic categories like this. Metal forming processes like casting, forging, drawing, sheet metal and other things. So then the second category, it will be metal removal processes. So where turning, drilling, milling, so all these things are called as the conventional manufacturing processes. And then we have the grinding, polishing and honing, which are the finishing processes. And also we have another set of processes which are called as the unconventional manufacturing processes. So where we have process like EDM, electrical discharge machining, ECM, where electrochemical machining, LBM, laser beam machining, and USM, ultrasonic assisted machining. And like this, so we have what is called as the of the conventional manufacturing process is that, so in conventional manufacturing, the tool should be harder than the workpiece material. So the tool should be harder than the workpiece material. So otherwise, we will not be able to make the cutting. And in unconventional machining processes, so the tool can be soft, but the workpiece can be hard. So thus, nowadays, when we talk about the advanced manufacturing process, so people are preferring more unconventional machining process because we have a lot of materials which are very hard to machine, but they are required. For example, if you take titanium and its alloys which have been used in the jet engines, so they are very difficult to machine materials. Their melting points will be around 2000 degrees centigrade. So when you want to machine them, it is very difficult. So we go for laser machining or EDM and other unconventional machining processes. Then we have another set of manufacturing processes which are called as additive manufacturing process. See, usually in metal removal process, we take the very big material and then cut the material and we remove that. So then we are wasting a lot of material. So instead of that, the principle of additive manufacturing is that, so when we want to, whatever the material we want, only there we are going to build. An example, if you take the civil engineers, when they want to build a house, so they put the bricks and then make the wall wherever it is required. So thus, even in mechanical engineering, so these kind of a concepts have come, and now the term what is called as a 3D printing is very, very popular. So whatever you want to print, so right from the mechanical components like gears or even the rotating part, or you can see here the intricate shape. So where with a conventional manufacturing, you can't manufacture a ball within a ball or a structure within a structure. But by using additive manufacturing, you can do that. So thus, nowadays, not only in engineering, but even people say they can print the cakes with the photograph or with your names printed on that. And in China and in other countries, they have been even 3D printing the houses. So you can use the concrete and then you can 3D print the whole of the house by using this kind of a technology. So you can go in the morning, tell the place where you want to build a house. So by the time you come back in the evening, you can see your building. So that quick you can make it. And also actually even painting is not necessary. So you can mix your paint in the concrete and then finally your complete house will be ready. So this is about the basic processes. So I'd just like to interact with you for a moment and then we'll go ahead. I think there is one college which is MET, MIET or MET. Are you able to listen to me? MIET is the metal machining. So it consists of forcing a cutting tool of harder material through the excess material. So what is basically metal cutting is, so we take a hard tool and then we move it on the softer material, and that enables actually cutting of the material. So it is like you take a sharp knife and then scratch it on any surface. So metal cutting is basically nothing but we are scratching it, but in a controlled way. So here you see two pictures. So the first one actually is the operation, what we call it as the turning operation. So where we are using a single point cutting tool. And on your right, what you see is a milling process. What is happening? It is called as the multi-point cutting tool. So where there are more cutting edges which are involved in the machining process. So here also you can see the single point cutting tool. So where there will be only a one point. So this is the point here which will contact the workpiece. But to literally to say it is a single point, it may not be correct, because in case you have only a single point, so it quickly wears out, and then actually a small line contact will be established. So that is the reason, though literally we call this as a single point cutting tool, but there will be what is called as a nose radius. So a curvature is given so that it is not a single point, but it is a line contact which makes between the workpiece and the cutting workpiece material and the cutting tool. So in the bottom, what you can see is the multi-point cutting tools. So the examples will be the drill bits, the milling cutters, then broaching and other operations. So where it is not a single point which makes the contact, but it is the multiple points. And also when you look at the single point, it is a continuous cutting. So you have probably done practicals in your first year workshop. So where you might have machined something by using the lathe machine. So where a single point makes the contact and then the material is removed. But if you look at milling operation, so you will have a cutting tool and then there will be several edges, several cutting edges, and then there will be a transition from one cutting edge to the other cutting edge, and then in between there will be a gap. So that is called as an intermittent cutting. So thus in a single point it is a continuous, but in multi-point generally it will be an intermittent cutting which will be taking place. So thus later when we talk about the cutting forces and cutting dynamics, so these aspects will be coming into picture. So now we'll go into detail about the turning process. So where it is called a single point cutting tool which removes the material from a rotating workpiece to form generally axisymmetric workpieces. Do you know what is an axisymmetric workpiece? Have you studied in your engineering drawing probably what is the solids of revolution? So where you have an axis, so when you draw a profile and then rotate it about an axis, so you can generate different types of shapes. So the cylindrical components and also the conical components, so they all come under what is called as the axisymmetric rotational components. So where when you rotate them, they'll be symmetric about an axis. So thus these kind of a cylindrical parts we can produce by using the turning operation. So there are various aspects of the turning process. So some of these things are mentioned here. You need to remember these points. So one, it is the workpiece. So what we have here is the workpiece and the cutting tool here. Then we have what is called as the rotation of the workpiece. So it will be rotating in this direction. Then we have the depth of cut. So where what is the amount of depth it should remove the material. So that is called as the depth of cut. And then we have what is called as the feed rate. So at what rate the tool should move parallel to the axis of this workpiece. So that is called as the feed. But if it is given in terms of like with reference to time, it will be called as the feed rate. So we'll come to the details of that. Then the initial diameter of the workpiece, generally it will be called as the D1, and then the final workpiece diameter will be called as D2. And then we have these cutting forces. So generally they'll be acting in this direction, that is the vertical direction. So in turning, it is actually a single axis, but though because of the other factors involved, there may be cutting forces in other directions, but the primary cutting force for turning will be in this vertical direction. So I would like to show a small video. probably if you can see that, you will understand it much better. If you have any issue, you can tell me. Otherwise, I'll show you this video.
The utmost importance when doing an effective cutting. In this video, we will provide a clear explanation of the cutting process and tool geometry. To remove a metal chip from a workpiece, you have to cut along at least 2 surfaces. Cutting along just one surface will not guarantee chip removal. For this purpose, cutting tools are provided with 2 cutting edges, a main cutting edge and an auxiliary cutting edge. The main cutting edge cuts the main portion of the chip, while the auxiliary cutting edge cuts the second surface and removes the material. You can see the smooth corner between these cutting edges. This corner is known as the nose of the tool. The radius of the nose greatly affects the surface finish of the operation and the strength of the tool. Material removal by the main cutting edge is easier when the material's flowing surface is at an angle. This angle is known as the rake angle of the tool, more specifically as the back rake angle. The back rake angle greatly affects the chip thickness and the force of the cutting. To avoid the rubbing of the cutting tool with the workpiece, a relief angle is provided as shown. Similar rake and relief angles are also given to the auxiliary cutting edge. A cross-sectional shape is shown here. Now, let's have a look at the tool's initial position. You can see that the cutting edges form angles, as shown. They are called end and side cutting edge angles. These 7 parameters together completely define the geometry of a tool. We hope you now have a conceptual overview of cutting tool geometry.
Process happening. So it is, I'll play it one more. This kind of a thing, it's not easy. We need high-speed camera, so with thousands of frames per second. So that is a kind of a camera which we need to capture these kind of images. So one of the university in US, so they have captured this image. So we can see it, how actually the chip is being formed. Now I'll switch back to the PPT. So where we have the feed motion in this direction, and then we have the cutting tool, the workpiece, the new surface which is generated, and rotation of the workpiece. So you are familiar with these terms now, workpiece and cutting tool. So the next important, very important term in the machining operation is a chip. So a chip may be sounding something different. It's not the chip what we eat, chips. No, these are metal chips, so which are actually play a very important role. So many times when people want to know whether the machining process is going on well or not, you know what they see? It is not at the machine component, but when you look at the chips, we can understand much better how the cutting process has taken place. So these chips are nothing but the small amount of unwanted material, so which is being actually removed from the basic workpiece. Then another term is important here, what is called as the cutting speed. So cutting speed is defined as the speed between the point, the single point what we are talking about, and the workpiece. See, now this is actually a rotating workpiece. So probably you can understand it better when you have a plane component and then a tool is moving linearly. So that you may understand it much better. So the speed, the relative speed between the workpiece and the cutting tool. So that is actually the cutting speed. So here in turning process, we have a rotating workpiece, that is the rotational speed. So generally the rotational speed we tell with reference to RPM. that is revolutions per second, or M is per minute, revolutions per minute. So when we have that revolutions per minute, we need to calculate the linear velocity. So we have a formula, so by using which we are going to do that. So that will come back, but for the time being, so you remember what is cutting speed? It is the relative motion between the workpiece and the cutting tool, and with what speed it is moving. So in this case, actually the tool is stationary and the workpiece is moving. In some cases it can be the other way, so the tool might be moving and the workpiece can be stationary, but anyway the relative motion between these two will be called as the cutting speed. So generally it is given in terms of millimeters per second, but in some cases it is also given in terms of meters per second or meters per minute. Generally they will use it when the cutting speeds are very high. Then we have what is called as the feed rate. So as already I have said, this feed is a linear feed along the axis of the workpiece. Okay, along the axis of the workpiece. What we give perpendicular to the workpiece, it is called as the depth of cut. But the feed rate, what we give along the axis, it is called as the feed. So generally feed is given in millimeters, but feed rate is given in millimeters per minute or per second. So based on that, you need to make the calculations. You'll be solving a problem at the end of this class. So you have to be careful with the units. And as I said, depth of cut is nothing but the depth what you are going to give perpendicular to the axis of the workpiece. Then the important aspect in turning is to calculate what is the material removal rate. So generally it is called as MRR. So what is the amount of material removed? So that is very important, because the economics and the time which is required, these are all depends on the material removal rate. So generally people want to remove as much material as possible in the shortest possible time, so that you can complete the work fast, but that generally doesn't work that way. So what people do is, in the beginning we give what is called as a coarse cut, so where the depth of cut will be more, and then we slowly rotate the workpiece and remove the material. In that case the amount of material removed will be more, but the surface finish will not be good. So finally what we do is to give a final and a finishing cut. So the depth of cut will be less, but the rotational speed will be very high. So probably, I don't know if you have done the turning in lathe. So if you do that, you find that you get a very fine mirror-like kind of a shiny finish. So thus, to increase the material removal rate, initially we do the coarse cut where large amount of material is removed, and when you are close to the required dimension, so when you want the finishing cut, a small amount of depth of cut will be given, and then high rotational speed will be given, and you can achieve a very good material removal. And when you are making these calculations, so the aspects what I have said are important. So cutting speed, so it is cutting speed or cutting velocity, which is millimeters per second, and then feed, it is millimeters, but millimeters means it is per revolution, millimeter per one revolution. But if you want to calculate the rate, it will be mm per second, millimeters per second or millimeters per minute. So feet, then if you are telling it with reference to time, it will be called as the rate, feed rate. Then depth of cut, generally it will be in millimeters. So in a rough turning, like you can have 1.5 millimeters or 2 millimeter depth of cut, but then for a fine finish it will be less than 1 millimeter, that is few micrometers, like 0.5 millimeters or 500 micrometers. Then the material removal rate, it will be given in terms of cube per second or per minute. So millimeter cube, that is the volume of material which is removed per unit time. So volume of material which is removed per unit time. So if you remember that, you will not make the mistakes with the unit. So here generally it is given in terms of millimeter cube per second. sorry, now we have a problem, so which you can solve. I think there was a small issue with this. Okay, so can you look at the problem and can you solve it and tell me the answer? Either you can send it through your chat or you can tell me orally. Can you note down this problem? But you can take it as in the turning process of a mild steel rod of 50 millimeter diameter, that is your D is 50 millimeter, then feed is 0.8 millimeters. So as I said, feed means 0.8 millimeters per one revolution. Then depth of cut is 1.2 millimeters, and the work rotational speed is 70 RPM. RPM is nothing but revolutions per minute. Now find out the material removal rate. Now find out the material removal rate, that is MRR. So I'll just show you the formula, the previous slide. So you can note it down and then tell me what is the MRR, what you are going to get. When you are done, you can unmute your mic and then tell me the answer, or you can, in other problems when you solve, this plays a very important role. So where generally students make mistakes is while calculating the cutting speed, V. How do we get this formula? You don't need to remember. So when we are cutting in one rotation, so the length, when you take a circle, cut it and then make it straight, what will be the length? It will be pi d, the circumference of it. So thus for one rotation, it is the length which is traversed. So pi d is the formula. Then you are rotating it for number of rotations, that is n. So number of revolutions per minute or per second. So that we are multiplying. And then we have 60. But probably if you look at our textbook, in some places, you will see that the formula for cutting speed is pi d n by 1000. Then you may be wondering, what is this 1000? Okay, you may not see the 60 there, but you see 1000. It is nothing but when you have given the units in millimeters, so when you want to convert them into meters, so they put divided by 1000. So thus, if you want the cutting speed in meters per minute or meters per second, so there you see that 1000. And whenever you want it per minute, so you will find that when the feed rate is given in millimeters per minute, to convert into millimeter per revolution, so we are going to divide it by RPM. And then when you want to convert it per second, so we are going to divide it by 60. So all these things are important, but the easiest way is you put your units whenever you have a formula there. So D is in millimeters. So N, have you given it in revolutions per minute or per second? So you can look at that. If it is in per minute divided by 60, so the resultant will be per second. So if it is in millimeters, then you want it in terms of meters, then it will be divided by 100. So you see different types of formulas in the textbook. Don't get confused. So in some places it will be like pi d n by 1000. In other place you see that pi d n by 60. In some other places you may also see pi d n by 60 into 1000. So don't get confused, be careful with the units. So now once you get the cutting speed, so we'll get 183.25 millimeters per second. So we are trying to keep everything in millimeters per second. So that will be much easier so that you don't make the mistake. So in case, for example, if the depth of cut is given in micrometers or anything, so you convert it into millimeters, and RPM, revolutions per minute, you can make it into per second and then keep it. So thus when you multiply cutting velocity and then the feed and the depth of cut, so you are going to get 175. So though this is a simple problem, but we spent enough time, so that you will not make the mistake basically in the cutting speed. Okay, so now there are different types of cutting, the basic cutting. So these terms are actually very important. So probably if some of you are writing GATE examination or going in for some of these competitive exams, so here these two terms, one is called as the orthogonal cutting, and then the second term is called as oblique cutting. Remember, first one is orthogonal cutting and the second one is oblique cutting. So what is this orthogonal cutting? So now here the figure what you see here is about the linear way of cutting. So in turning actually you see a cylindrical workpiece and a single point cutting tool. In order to explain the concepts of the cutting process, so they just make it linear. So you find that the workpiece is like linear workpiece like this, and then the cutting tool is moving in this direction. That means it is moving in the in an axis parallel to the workpiece, so in a linear direction. So these are concepts. So practically when you look at the turning process, so you find that you have a rotational cylindrical workpiece and then tool stationary there. But to make it simple, so this is the diagram what you see. Now how do you define this orthogonal cutting? I think you would have studied the engineering drawing, you know what is ortho. Ortho means 90 degrees or perpendicular. So that is what it is meaning. So what is 90 degrees here? So what we see 90 degrees is if the line axis of the workpiece if you draw, and then if you see the cutting edge and then how it is moving, so they are 90 degrees to each other. So here we see this, the workpiece, and then this is 90 degrees. So you can see the 90 degrees here. So the angle between the cutting edge, which is this one, and then the workpiece, or that is actually the axis along the workpiece in which the tool is moving. So the tool is moving and inclination of the cutting edge to that axis. So that is 90 degrees. So when it is 90 degrees, it will be called as the orthogonal cutting. So in this orthogonal cutting, the direction of the chip flow velocity is normal to the cutting edge of the tool. So which is the cutting edge? So here we can see this is the cutting edge. So it is perpendicular to that. Then here we have two components of the forces which will come into picture. One is the cutting force and then the other one is the thrust force. So in this direction the cutting force, and this direction it is the thrust force. So only we have two cutting forces which will come into picture, and primary cutting force is this cutting force. Then the thrust force is the secondary one. And this type of cutting where it is happening in only two dimensions, so it will be called as a two-dimensional cutting. So where only two forces we have in two directions which are perpendicular to each other. And this is about the orthogonal cutting. But you need to understand a fact here. No cutting process is a completely 100% orthogonal cutting. So it is not completely orthogonal. So when you look at even turning, when you look at the tool angles, when you take them into consideration, and also the tool nose radius, the contact angle, all those things, so it is not 100% orthogonal cutting. But to make it simple, it has been called as the orthogonal cutting, and many of the models, so generally we simulate the cutting forces, and when you want to simulate this kind of a process, so we assume it as an orthogonal process, and then we calculate all the formulas and everything, because that is more simple to understand the basic concepts of it. But in practice, the cuttings will be in the oblique way. So you can see here, so this is along the workpiece, this line is the direction of the tool movement V, what you are seeing. And then the axis we can see here, it is not 90 degrees, but it is inclined with a particular angle. So this inclined angle alpha, this is called as the angle. What is that angle? Okay, so the cutting edge is inclined with an acute angle to the direction of the tool of the workpiece. So this, when you have that angle, it will be called as the oblique cutting. So this in oblique cutting, we have the three types of cutting forces which will come into picture. So one is the primary cutting force, then the second one is the radial force, and then we'll have the thrust force, or it is also called as the feed force. It is also called as the feed force. So now, whenever we have the turning process which is happening, maybe in your colleges, if you have the dynamometer, a 3-axis or a 3-component dynamometer, you can mount your tool on that, and then you do the cutting process. You find that the cutting force will be maximum. Then the radial force and thrust force, it will be there. It is not zero. If you can have a cutting process, so where if the radial force and the feed force on your instrument, if it is reading absolutely zero like a line, and only you see the cutting force which is at a high level and which is there, then that will be the orthogonal process. But generally in practice, you won't see that, because here you have the tool angles and then the inclinations and all these things. So thus all the processes are oblique cutting processes. So now maybe even in your exam there may be a question which can be asked, what is the difference between an orthogonal cutting and oblique cutting? So you should be able to clearly tell what is the difference between these two processes. So now, how we are getting that oblique cutting? So when you look at the geometry of the single point cutting tool, so you will understand it. So these terms are very important, and also in many times in examinations and even in competitive examination, they will ask these kind of questions. So what are the nomenclature of these tools and the tool angles, so which you are going to see later. So they become very important. So the nomenclature is that, so generally this part of it, so what you see is called as the shank. So this is the shank. So why we need the shank? To fix the tool on the tool post, we need the shank. And then we have the face. So how do they produce these single point cutting tools? There are different types of tools. So this is actually a ground from a blank of tool. So there will be a rod which may be generally made of HSS. So HSS is nothing but high speed steel, so which is a hardened steel. So where many tools are made with that. So you have this tool blank, and then we grind it to the required angle so that we get the cutting edge. But nowadays we have what is called as the tool inserts, so which are only a small pieces of inserts, so which can be fixed on a tool holder, and then you can use it. What is the advantage of that is, whenever this tool becomes blunt, we need to remove the tool, take it to what is called as the tool room, so where there will be a tool and cutter grinder. So we have to mount it on that, so regrind it, then again we have to bring it back, fix it on the tool post in the lathe, and again we need to start the machining process. So this actually causes a lot of waste of time, which is not desirable in a shop floor. So thus what they do nowadays is the inserts, so where the tool post will be, tool holder will be fixed on the tool post, and then whenever the insert is worn out, you can actually index and use the other cutting edge, or we can remove it and then replace it quickly with another tool insert. But anyway, so this what we are seeing is the one blank of tool which has been ground to this shape, and this is called as the tool face. And we have the flank faces here. So this is the front flank face and the side flank face. So when you ground it to this kind of a shape, so we get what is called as the cutting edge. So this is the cutting edge. And then we have this here at the corner, so there will be a nose radius. So as I said earlier, though we call this as a single point cutting tool, but we have a cutting edge. So where even that part also removes the material. And then we have the nose radius. So this one which also makes the contact and removes the material. So thus no cutting operation is exactly a single point cutting tool. Even if you make a single point cutting tool, that means a very sharp one, So as soon as you start machining it, so it wears out and then it becomes again a line contact. So thus this is the cutting edge and a nose radius is here, and this is called as the side cutting edge, and this is the end cutting edge, and the nose, which is the cutting point. Then this part of it, the bottom side, it is called as the heel. So remember this terminology: shank, then face, then flank, then we have end cutting edge and side cutting edge, and then we have the nose. So here we see the 2D sketch of the cutting tool. So where we have different definitions. So where this is the point or the cutting point. So wedge shaped portion where face and flank of the tool are meeting. So this is a point, or you can call it as a cutting point, where primarily the cutting takes place there. Then we have the base part of it, or the shank. So this is the base which sits on the tool post in the shank. Then the nose radius, so where we see the nose radius here. So that is the cutting tip which carries a sharp cutting point. So nose provides a radius, so it can't be straight, so it is a nose radius. Then the typical value of this nose radius can be 0.4 millimeters to 1.6 millimeters. So smaller the cutting radius, so we find that the edge will be becoming blunter. So we need to be careful in selecting the nose radius. So single point cutting, and then we have the angles which are very, very important. So the first one is called as the side rake angle, and then we have end cutting edge angle and the end rake angle. Okay, so maybe here in this diagram you can see better. So can you see this? So the rake angle. So generally it will be back. So that means it is inclined backward. So that is the reason it will be called as a back rake angle. So in few cases where the cutting edge strength is required, only in that case it will be positive, otherwise it will be negative. So that is the reason it is a back rake angle. And then this angle is called as the wedge angle. And then this angle is called as the end relief angle. So why end relief angle is required? So whenever you are machining, think that you have a cylindrical workpiece and this point is making contact with the workpiece. So the surface of the cylindrical part should not rub with this edge. So that is the reason actually it is slightly taken in, otherwise it will be rubbing the surface which is formed. And then back rake angle also, the chips which are actually formed will be flowing on this face portion of it. So this will be having a negative angle, so it is a back rake angle. Then the wedge angle is important. So if these angles are very large, then when the wedge angle becomes smaller and smaller, so the tool actually becomes weak. So whenever you are cutting very hard material, so it cannot have the weaker edge. So you need to balance between the angles, otherwise the cutting edge, when the wedge angle comes smaller, so it becomes weaker. So we need to be careful about it. So remember, rake angle, it is the back rake, so generally it will be towards the back, and then we have the end relief angle. And then, so here we have the end cutting edge angle. So you have seen what is the cutting edge. So that edge also, if it is like perpendicular, so it will interfere with the workpiece. So it is a small angle is given to give the clearance. So that is called as the end cutting edge angle. And then side cutting edge will be here. So even that is also given a clearance there. So it is called as the side cutting edge angle. And then nose angle. So here we have the nose radius. and this angle is called as the nose angle. So these are the cutting angles, and one more angle you can see here, side rake angle from a different view and side relief angle. So these are various angles, so which have been given in the 2D. So probably you can understand it much better. And this figure is very important. So many of the examinations you find that they will ask this kind of a question. So draw a neat sketch of the single point cutting tool and indicate various angles in a single point cutting tool. And also sometimes they can ask even the nomenclature like shank, base, and then the cutting edges, all these things. Then the angles are very important. So what you see here, you can see these things in much better way in the 2D diagram. So the rake angle, back rake angle. So it is inclined backwards, so it is a back rake angle. It is the rake angle. And then we see here end relief angle. So this is the end relief angle, and this is the end clearance angle. So why end clearance angle is given is that, so it should not interfere with the surface which has been newly formed. So this edge what we have, so draw a line here. So this angle between these two is the end relief angle, and angle between this edge and the vertical line, it is the end clearance angle. Then the lip angle, so what you see here between the back rake angle line here and the relief angle line here, so this is the lip angle. And then we have the nose. This is the front view and this is the top view of it. So we have the nose radius here. So we have the nose, and then we have the cutting edge here, and this angle is called as the end cutting edge angle, and this angle is called as the side cutting edge angle. So side rake angle also is seen here. Side relief angle has been shown from a different view. So this diagram, probably you should remember it and it should go into your mind. So this is very important from the aspects of understanding the machining process and also from the point of examination. Okay, I think these definitions PPT will be sending it to you, so you can see what these aspects are. You can remember that. Then here we have a positive rake angle. So what is this positive rake angle? What is going to happen if you have a positive rake angle or increased rake angle? Reduces the compression, the forces and the friction, yielding a thinner and less deformed and a cooler chip. So based on the type of rake angle what we will have, so it has the influence on the type of chip what we have. So here the cutting forces and the friction will be less, and the yielding a thinner and a less deformed chip, which will result in a cooler chip. But increased rake angle will reduce the strength of the cutting tool. So the tool section becomes smaller, so it reduces the strength and heat conducting capacity. See, another important aspect in this machining process is that, so when the material is being removed, heat gets generated, and it will be maximum at the tool and the workpiece interface where the chip is going to be formed. So how do you remove that heat? So probably sometimes you would have looked at the machining processes, you see the workpiece becoming red hot, and nowadays we have the cutting tools with a very high hot hardness, a term called as hot hardness. That means even with at higher temperatures, so they retain their hardness. So thus, even when it has become red hot, still we can see that the hardness is maintained and the machining process goes on. But how do you remove that heat? So basically the chip actually carries a lot of heat along with it, and then heat is removed. And the tool also actually, the shank part of it, it takes away the heat, and the workpiece. So thus the heat is being removed by the chip, the tool, and also the workpiece. Otherwise, the temperatures will be highly uncontrollable, and the properties of the workpiece material and also the tool changes, which is not desirable. Then, what is going to happen if you have the negative rake angle? So, to provide greater strength at the cutting edge and the better heat conductivity, generally we go for the negative rake angle. So, it is generally being employed on carbide and ceramic and polycrystalline diamond, that is PCD. It is called as a PCD tools, polycrystalline diamond. Actually, diamond, as you know, which is the hardest material. So if you can have a diamond tool, that is the best, but the natural diamond is expensive. But we can produce the artificial diamonds. So by using a polycrystalline diamond, we can have a PCD tools. And also polycrystalline cubic boron nitride. So it is called as a CBN, cubic boron nitride cutting tools, which are becoming popular these days because they give a very good surface finish, and also the tool life will be high. So CBN tools. So this term you can remember, PCD tools, CBN tools, which are very advanced tools. So these CBN tools are also polycrystalline cubic boron nitride, PCBN tools. Then it increases the tool force, but this is necessary to provide added support to the cutting edge. So whenever we are cutting the hard materials, so this is good, otherwise the strength will be decreasing. So negative rake or a small rake causes high compression, then high tool forces and friction, resulting in a highly deformed chip. The chips will be very hot. So negative rakes are all recommended on tools which does not possess good toughness. So low transference rupture strength when it is there. So we are going to provide with the negative rake angle. Zero rake. So you can see this one, it is exactly vertical like this. So a tool which has a zero rake has no rake is provided on the tool. Zero rake increases tool strength and avoids digging to the tool into the workpiece. It's good. Like brass is turned well with the tools having zero rake angle, but generally it is not good for the other materials. So we go for negative rake and not the zero rake. So very rarely we use the zero rake. So remember that what is the use of having a positive rake angle, negative rake angle, and zero rake angle. So sometimes you may have an objective type of questions which will be asking for what material and for what tool. So which type of rake angle is recommended. So this is about the rake angle. So then we have what is called as the lip angle. So lip angle is nothing but the angle between the face and the flank of the tool. So this is called as the lip angle. It is also called as the angle of keenness of the tool. So larger the lip angle, stronger will be the cutting edge, and vice versa. So if you have a larger lip angle, so we'll have a greater strength. But again, the other angles get affected, so you can't get good edge angle and then relief angle. So you need to know what should be the lip angle. So similarly, we have the relief or the clearance angles. So these are ground on the end and the side face of the tool to prevent it from rubbing on the workpiece. So that is the basic concept. So why we have these relief angles? To enable only the cutting edge to touch the workpiece and cut freely without rubbing against the surface of the job, either the original surface or the newly formed surface. So side relief angle, ground directly below the cutting edge on the flank of the tool. And end relief angle, so angle grounded from the nose of the tool. So these are the other angles. So where we have the cutting edge angle, then side cutting edge angle, and end cutting edge angle. So what is this cutting edge angle? So it's ground on the tool so that it can be mounted in the correct position for various machining operations. So cutting edge angle is important. Then side cutting edge angle allows flank of the tool to approach the workpiece. So first, that face is going to come first. Then spread the material over a greater distance on the cutting edge. So all these angles are very important. And obviously the nose radius is the rounded tip on the point of the tool. So what are the functions of this nose radius? This is again very important. So this strengthens the finishing point of the tool. So otherwise it will be an edge which gets worn out. Improves the surface finish of the workpiece. Then it should be twice amount of feet per revolution. So this is very, very important. So whenever you are cutting a workpiece and when you are deciding what should be the feet, so the cutting nose radius becomes important. Actually in macro cutting, so what is the general type of cutting? So this is not important, but we have what is called as a micro machining. So wherein the dimension of the cutting tools is few micrometers. So I'll show you maybe later how even you can drill a hole in the hair, human hair, you can drill a hole. So about 30 micrometers or 50 micrometer diameter. So when you have that kind of a technologies, so the nose radius becomes very important. So the nose radius should be twice the amount of the feed what you can give. So thus feed and the nose radius becomes important. If it is less, what is going to happen is cutting will not take place, and there are other concept which is called as a ploughing which is going to take place, and still further smaller it will be a rubbing which will be taking place. So not the cutting. So thus the nose radius should be twice the amount of the feet per revolution. So large nose radius may cause chatter because it becomes blunt. So thus it may causing the chatter. You know what is chatter? So these are another important question which generally will be asked. There are two terms which is called as vibration and chatter. So vibration is a periodic motion because you have a rotating head and the moving parts. So you get what is called as the vibration. It will be a more periodic. But chatter is abnormal increase in these vibrations. So that can actually result on the workpiece a very rough surface. So that's what I said. When you look at the chips and also at the workpiece, you can know how the machining process taken place. If the chatter are caused, then you find that the marks, chatter marks on the workpiece, and which is not actually good. So thus, if the nose radius is large or the tool actually becomes blunt, to say in other terms, the tool has become blunt, then the chatter will be there. Then small tool nose radius weakens the tool strength, so thus it wears out very soon. For rough turning, it is kept about 0.4 millimeters, and for finish turning, it will be 0.8 to 1.6 millimeters. So this can be used as the guidelines. Okay, I think we'll be stopping here for today, and we have few videos which we tried to show you in the last class. So I think there was no sound and some people couldn't see the video. I'll be showing them. But before that, I want to ask you if you have any doubts or questions, can you ask? Can you please unmute the mics, and then can somebody interact? Were you able to understand, or anything that we need to stress more? Can you please unmute the mics?
The next time you...
Yeah, can somebody speak? Now what you see on the screen is only the video which I am going to show next. But before that, I want to listen from you whether you are able to understand or any point need to be elaborated, or your feedback.